Okay, now we can move on to shared resource design for a multi-core system. This is a very exciting area, and have lots of works to cover. I don't think we'll be able to cover all of them. If you look at a multi-core system, these cores are supposed to be red, but the red part is very small. If you look at most of the system, most of it is really shared resources. And the design of them is very critical for the performance. So what are these shared resources? When you look at a core, it includes the L1 private caches, so I consider them as part of the core. But they're shared L2 caches. They could be distributed across the cores if you want a scalable multi-core system. There's shared interconnect, some sort of interconnect. There are other shared caches. There's shared memory controllers. There's shared pins. There's shared main memory. And there's shared storage and links to the storage. So pretty much most of the system is shared. And I don't have the picture right now of the other real chips, but if you look at the real chips, most of it is really shared among the cores. So it's very important to manage these shared resources. So why are these? Well, these don't need to be shared, right? But the resource sharing is important. The key idea is instead of dedicating a hardware resource to a hardware context or a core, we allow multiple contexts or multiple cores to use it. I said multiple contexts here because you could have this in a multi-threaded processor also. In a multi-threaded processor, you have multiple contexts. There are many resources, functional units, pipeline, caches, buses, and memory. And functional units are shared between different threads in a multi-threaded processor. So you could take the resource sharing to the extreme in a multi-threaded processor. Well, why do we do this? The reason is simple. Resource sharing improves utilization and efficiency, which leads to hopefully higher throughput. When a resource is left idle by one thread, another thread can use that resource. There's no need to replicate the shared data. So the resource could be a time resource or a space resource. You can use things in time and space when it's left idle. This also reduces communication latency. If you share resources, you can keep, for example, shared data in the same cache in an SMT or a multi-core processor. That way you reduce the communication latency. And also this is compatible with the shared memory model. Shared memory implicitly assumes that, well, you don't really have to have a shared location physically. Again, as I said, you can have distributed memory and you can implement the shared memory abstraction on top of it. But this is having a shared resource is the most compatible with the shared memory model, with a single global address space. There are disadvantages to it, of course, also, right, with any design decisions you make. It results in contention for resources. When the resource is not idle, another thread cannot use it. That's the problem. If space is occupied by one thread, another thread needs to reoccupy it in a cache, for example. As a result, this sometimes reduces each thread's or some thread's performance, and thread performance can actually be worse than when it's run alone on the same system. And we'll see a lot of examples of this. This eliminates, sharing the resource eliminates performance isolation. You can get inconsistent performance across different runs of the same application because it may be sharing resources with different threads at different times and there may be different interactions. Uncontrolled sharing degrades quality of service because of this reason. If you don't control the sharing somehow, if it's free for all, if any thread can get the cache block that it needs, you can get quality of service degradations. And this is important, as we will see, because the user gets affected by it. Service level agreements get affected by it also. And this can cause unfairness and starvation, as we will see in many of the shared resource management issues. Basically, the key takeaway is we need to efficiently and fairly utilize these shared resources. A resource sharing, if it's not done in an intelligent way, can be inefficient because one thread may be, let's say you have a streaming thread that has a huge working set. It may be occupying the entire cache and it may not be benefiting from that cache at all. Whereas there's another thread that has a very small working set that would otherwise nicely fit in the cache may be getting evicted out of the cache because of this huge thread that streams in data. So you need to be efficient in the management and you need to be fair in the management. And sometimes these are very tightly coupled. If you're efficient, you can be fair also because you may not want to allocate resources to threads that do not utilize the resources well. But these are not always, they don't always go the same way, and we will see examples of it, hopefully. So I'll just have a slide on the need for quality of service and shared resource management. Why is unpredictable performance or lack of quality of service bad? We will get to this later on. Because if you have lack of quality of service, if you have unpredictable performance when you're sharing resources, this makes programmers' life difficult. Again, a lot of things go back to the programmer. We don't want to make programmers' life difficult. A programmer may be optimizing their program very well to fit in the cache, And they can get very low performance because there could be another application that's getting rid of all of the blocks of that application in the cache. This also causes discomfort to the user. An important program can starve. It's actually true for software resources also. For example, when you're running an application that's important to you, if the virus scanner can come and hog all the resources. It could hog the memory. It could hog the storage. And Microsoft has always had problems with these software resources that are shared. An unimportant program gets a lock, and an important program, as a result, cannot make progress because it's waiting for the storage lock or some kind of software lock. It's the same thing in a hardware resource also. You can think of a hardware resource when it gives priority to another application, it's being locked by that other application, right? And this also makes system management difficult because how do you enforce a service level agreement when hardware resources that are shared is uncontrollable, right? We would like to provide a guarantee in terms of performance. Even if it's a soft guarantee, you cannot provide this if you cannot control that hardware resource sharing. So we'll take a look at those, how to actually provide quality of service in shared resources later on. So there are two things, resource sharing versus partitioning. Partitioning is the other end of the spectrum. All of the resources are partitioned. Sharing improves throughput. It gives you better utilization of space. On the other hand, partitioning provides performance isolation, right? You know what performance you're getting if you partition the resources. You may not be getting the highest performance because you don't have all the resources available to you, but you know what performance you're getting exactly because you get predictable performance. You get dedicated space. The key question is actually, can we get the benefits of both? And the idea that we will explore is to design shared resources such that they're efficiently utilized, controllable, and partitionable. Now again, efficiently utilized is not necessarily, does not necessarily tackle the question of sharing and partitioning. So we'll start with this efficient utilization first, and then go into sharing and partitioning issues. Basically, we would like to ensure two things. One is no wasted resource. If you have a cache space, you want to utilize it very efficiently. You don't want to have a block that's occupying a cache space that's not going to be used. That's what you would like to do ideally, right? And today's systems, if you look at today's systems, I don't think I have the data on the slides, but even in L1 caches, more than 60% of the data is useless. Meaning it's there dead, sitting there dead. It's not going to be touched. And that number is even higher in the L2 bigger caches. And we would like to also have quality of service mechanisms for different threads, such that they can get the performance they need. What are these shared hardware resources? The memory subsystem in both multi-threaded and chip multiprocessor systems is shared. Non-private caches, interconnects, memory controllers, buses, and banks. The I/O subsystem is, again, shared. I/O, the AMA controllers, Ethernet controllers, they're all shared. And processor is shared in case of multi-threaded systems. The pipeline resources and L1 caches are also shared. So a multi-threaded system has the resource sharing to the extreme. So one issue in caching, so let's take a look at the example of caching first, and then we'll hopefully get to interconnects. And next week when we talk about memory, we'll talk about memory controllers, buses, and banks. And I don't think we'll ever get a chance to talk about I/O, but that's also important, especially going forward. We have the emerging technologies that look more like the non-volatile technologies that I briefly talked about earlier, that look more like memory. And going forward, memory and storage will merge, in my opinion, and they will look very similar. So maybe we won't have flash memory as the I/O subsystem, but it's as part of the main memory system going forward. Okay, so how does the cache hierarchy change in a multi-core system? If you have a single core, you don't have the choice of sharing versus partitioning, right? Unless you have multiple threads. But you can have a private cache, in which case the cache belongs to one core. This is the example here. And a shared block can be in multiple different caches. So it's, if you're sharing a block across different cores, that shared block is replicated. And you can also have a shared cache. In this case, the cache is shared by multiple cores. So shared block occupies a single space, which means that this is more efficient for shared blocks, right? So there are advantages and disadvantages to both approaches at the fundamental level. The advantages for shared caches over private caching is you get high effective capacity, right? Because you don't replicate these blocks. And you get dynamic partitioning of available cache space there's no fragmentation due to static partitioning, right? Assume that these are all 1 megabyte cache and this is a 4 megabyte cache. If this core needs only 1 block and this core needs 3 megabytes of cache, here you cannot satisfy both, right? Here you can satisfy both nicely because you can dynamically partition the space. So there's no fragmentation. And this is true for all kinds of sharing versus partitioning decisions. Whenever you share, you get dynamic partitioning. It's easier to maintain coherence also. A cache block is in a single location, right? Here, actually, you don't have a coherence problem here, in the L2 cache at least. Here, you need to maintain coherence across blocks. And shared data and locks do not ping-pong between caches because you have a shared cache again. But there are disadvantages to shared caches also. First, you get slower access because it's bigger. You cannot customize the cache for the core. Cores incur conflict misses due to other cores' accesses. These are misses due to inter-core interference. One core can evict a block of another core. And some cores can actually destroy the hit rate of other cores. I've already given you the example of a streaming core evicting the blocks of a core that has nice locality. And we'll try to fix that problem in the next few mechanisms that I'll describe. And the third issue is the quality of service issue. Guaranteeing a minimum level of service or fairness to each core is harder with a shared cache. With a private cache, there's no problem. In this case, you need to figure out how much space and how much bandwidth to provide to each core. And we'll try to tackle the space issue. Bandwidth issue is much more of a problem in main memory. By the way, main memory has the same issue. You can share or partition the main memory across different cores, and the same things apply here. Except in main memory, bandwidth is a much, much bigger problem than in caches because on-chip bandwidth is much higher than off-chip bandwidth. Okay, how do you share? Assuming that we're going to have shared caches, how do you share these caches? One option is to have free-for-all sharing, saying that we're not going to be aware of threads, we're not going to be aware of anything intelligent. Basically, we're going to use replacement and placement policies that are the same as a single core system. Basically, these are usually least recently used based replacement policies or some kind of pseudo least recently used based approximation to LRU policies. These are not aware of applications or threads, and these are also not aware of the potential reuse of a block, or they make a reuse prediction that say, if I've touched a block recently, I'm going to touch it again. That may not be a correct reuse prediction, right? For all applications at least, or for all access patterns. In this case, an incoming block evicts a block regardless of which threads the blocks belong to. So there are problems with it. One is you can get inefficient utilization of cache because LRU is not the best policy, and we're going to target that. And a cache-unfriendly application can destroy the performance of a cache-friendly application. And not all the applications benefit equally from the same amount of cache. Free-for-all might prioritize those that do not benefit. Again, the same example. A streaming application, it doesn't benefit, but it has a huge working set, and it evicts everything else from the cache. So as a result, you get reduced performance and reduced fairness because of free-for-all sharing. So we're going to tackle this problem. How do we actually more intelligently manage the cache? This is actually reordered in a way. You can control the sharing of the caches, and I will talk about some mechanisms later on when we get to it. One is the idea of utility-based cache partitioning. The other is the idea of paired cache partitioning. And the third is the idea of having sharing and private caches at the same time together, how to get the best of both worlds. But first, I will cover more efficient cache utilization. These two need to be employed together, I think. Efficient cache utilization means how do you design better cache management policies compared to LRU, least recently used, or compared to other policies like random replacement. Actually, in practice, it turns out across many applications and general purpose system, least recently used replacement is similar to random replacement. If you pick a block to replace randomly from a hardware cache, it's very similar to if you pick the performance you would get if you pick a block that's least recently used. Can anyone guess why? Because of different access patterns, right? And the reason is if you pick a block, if you're thrashing the cache, if you pick a block randomly, you'll at least keep some of the working set of the application inside the cache because you don't evict the least recently used. If you have a cyclic reference pattern, I'll give you one example. And this result is repeated over and over. And if you're interested, I'd encourage you to do the same experiment on your own. It's a fun experiment to do. But let's say you have 4 cache blocks to allocate, and your reference pattern is A, B, C, D, E. And you keep accessing this in a circular fashion. If you have least recently used replacement, the cache hit rate is 0%, right? Because you evict the blocks that you're going to access this way. Basically, you have A, B, C, D in the cache when you're accessing E. And when you're accessing A, you have B, C, D, E in the cache. When you're accessing B, you have C, D, E, A in the cache. As a result, you get 0%. Whereas if you have random replacement, you get a much better hit rate. And that could be a homework assignment for the weekend. So what is the hit rate that you would get with a random replacement? It's actually easy. But basically, you have 4 blocks, and you have the cyclic reference pattern, and you pick randomly what to replace. And I would argue that it's much, much better than 0%.
Because randomly you put A in your cache, but they are also operating.
That's right. Exactly. Yeah. Whenever, and this behavior is called thrashing. Basically, here you're thrashing your cache, right? You have more elements that need to go into the set than the set can provide. And this access pattern happens to be very bad for the LRU replacement. And you see this behavior a lot. If you imagine an array access, right? You're going through an array, and this is the array elements, and they happen to map. It doesn't exactly work this way. They happen to map to the same set. This is what happens, right? And many programs do this, and as a result, you get random replacement performs similarly to LRU replacement. And you can. Yes, I'm going to describe some better mechanisms. People have developed many better mechanisms, actually. Some of them are actually employed in existing processors. I'll describe some of the mechanisms that we have looked at. And people are looking at it for, hopefully, real processors today. But there are better mechanisms, definitely. People have looked at least frequently used. That doesn't work very well also. But people have looked at other mechanisms that I briefly talk about. You can identify, you can, for example, insert into the cache, insert blocks into the MRU position, most recently used position, high priority position, with low probability. So whenever you get a cache block and it's not in the cache, you flip a coin. With a very low probability, you insert at the MRU position. With a very high probability, you insert at the LRU position. This way, you keep most of the blocks in the cache. And that way, you'll be thrash resistant. But that's not the best policy. I'll compare to that policy later on. Okay. So let me first talk about something that I really